As quantum hardware scales toward fault tolerance, modeling error correction relies on mapping massive, high-dimensional tensor networks. But as these architectures grow to encompass millions of edges, they inevitably develop critical structural flaws. Look at this network model. When a central cluster dims and detaches, it creates a zero entanglement boundary, a topological dead zone that completely destroys logical qubit capacity. Tracing these isolated subgraphs across multi-million edge topologies currently forces hardware engineers to spend weeks manually identifying dead logical qubits. Identifying these bottlenecks has officially scaled beyond the limits of human engineering, demanding a new tier of automated diagnostics. Large language models offer the exact heuristic problem-solving capabilities required to diagnose and route these massive networks. However, physics is deterministic, and LLMs are not. If you drop an unconstrained AI agent into a quantum environment, it will suggest physically impossible patches that would silently corrupt the hardware blueprint. For instance, the AI might attempt to bridge a gap by connecting physical nodes that do not exist, or it might demand infinite physical upgrades, expanding the network's bond dimensions, represented by the Greek letter chi, far beyond reality. These non-viable heuristic patches cannot be deployed, but filtering them manually creates a massive engineering bottleneck. This is exactly why the TNQG Enterprise Diagnostics Suite was built. TNQG acts as a deterministic verification sandbox. It extracts the creative problem-solving of an LLM, but enforces the rigid laws of quantum topology. The TNQG pipeline begins by ingesting these massive tensor network payloads directly from the hardware blueprint. For the initial detection phase, the engine does not use AI. It relies entirely on native entanglement capacity calculations. The primary detection tool is the Boykov-Kolmogorov max-flow min-cut graph algorithm. This visualization shows how the algorithm works. Lines of varying thickness represent entanglement flow from source to sink. Watch what happens when capacity drops. The algorithm instantly pinpoints the exact edges causing topological isolation, generating a clear minimum cut. That isolated failure point is immediately flagged for hardware remediation. By using deterministic flow mathematics first, TNQG guarantees precision in locating the failure before any heuristic AI is ever involved. Once the bottleneck is mapped, TNQG automatically queries a commercial LLM via a REST integration. The LLM is tasked with generating a structural hardware patch to route around the dead zone, delivered back as a JSON payload. To prevent corruption, that raw AI patch is never presented directly to the hardware engineer or the hardware itself. Instead, TNQG utilizes a zero-copy clone, a simulated testing environment containing a structural wireframe copy of the isolated subgraph. The engine applies the AI's JSON patch exclusively to this clone, injecting new structural links into the simulation. Instantly, TNQG executes a high-speed physics proof on the altered clone. To pass, the physics proof must demonstrate a mathematically proven, verified improvement in entanglement capacity. This process ensures zero risk to the physical blueprint by neutralizing non-viable AI hallucinations within the simulation layer. A patch might work mathematically in a simulation, but still be physically impossible to build on the manufacturing floor. To account for this, the suite actively monitors the network complexity penalty during the physics proof. This chart tracks dynamic bond dimension over time. When the AI attempts an infinite physical upgrade, a rigid barrier blocks it, forcing the patch back down into a viable corridor. This tracking guarantees logarithmic entanglement capacity scaling, keeping the resource demands realistic. TNQG will outright reject any proposed patches that attempt to over-engineer the hardware with arbitrary physical upgrades across the circuit. Managing this complexity cost ensures the LLM's heuristic solutions remain tightly bound to the physical resources available on the hardware floor. Analyzing multi-million edge topologies requires an incredibly resilient backend capable of handling continuous flows of computational data. Standard setups fail under this pressure, crashing from Linux out-of-memory errors or global interpreter lock starvation. TNQG bypasses this using specific memory complexity defenses. Native Python yield generators and aggressive microbatching eliminate RAM spikes entirely. It also employs kernel-level deadlock protections, utilizing OS-isolated pipes and targeted zombie process annihilation. This architecture ensures the diagnostic server never crashes, remaining immune to the pathological graph loads it is designed to analyze. Hardware bottlenecks are pinpointed instantly, patched creatively by an LLM, and constrained by rigid physics protections. As a result, quantum islands that previously took weeks to trace are safely reintegrated back into the bulk network in seconds. The TNQG Enterprise Diagnostics Suite provides the infrastructure to integrate agentic AI directly into the hardware engineering pipeline under the protection of automated physics verification.